Kia ora koutou. In this video, I'm going to go through 3 of the questions from the booklet that I gave out in yesterday's class for level 3 differentiation. So the first one is one that we did in class, but I did it quite quickly and probably before some of you really understood how parametric worked. So I'm just going to slowly go through the whole booklet, starting at the start. I've videoed quite a few of these questions in separate videos, and you can go and find those if you want. But in this video, I'll try to emphasize the same things that I was talking about yesterday. So my first question here is a parametric differentiation one. This is from last year's exam. And we're given a curve, and it's got 2 equations. And the first one is this, x is equal to 2 plus 3t. And the second is y is equal to 3t minus the natural log of that. Now we're told that t is greater than 1/3. I didn't mention this in class yesterday, but we need this condition because remember that whenever we take the log of something, the thing that we're taking the log of has to be a positive number, right? Because this is my little graph of the natural log of x, and it's defined only for positive x values. And that's the same for a log to any base, right? The argument of the log has to be positive. So in here, we don't have t, we have 3t minus 1, and we've got to have that being greater than 0. And that's how we end up with t being greater than 1/3. Anyway, back to the question. And what we're asked to do here is to figure out whereabouts on the curve the tangent has got a gradient of 1/2. So we need to find dy by dx, and then we need to set that equal to 1/2 and solve, and that will give me a t value. And then we take that t value and we put it back into our 2 equations to get our x and y values. Okay, so I'll work through this one down here. So we've got x is equal to 2 plus 3t, and y is equal to 3t minus the natural log of 3t minus 1. So dx by dt is very easy to work out. It's just 3, and dy by dt is equal to 3 minus the derivative of the natural log is 1 over the thing, right? So that's why I've got 3t minus 1 in my denominator times the derivative of the inside function, which is 3, right? So I'm using the chain rule to differentiate that. Okay, now when we do parametric differentiation, what we're going to use is the chain rule. So what we're saying here is that when x changes, there's a link to t changing, and when t changes, there's a link through to y changing. Remember that parametric works like this. We have t affects x and t affects y, and because t affects both of those things, we indirectly get a link between x and y, and that's what we're usually interested in, dy by dx. But once you start doing parametric, you will very quickly learn that this chain rule setup means that I can now write dy by dt divided by dx by dt. So sometimes you'll see people write it as y dash over x dash. What we're going to do now is we're going to use this derivative and link them up to get this. So dy by dx is equal to dy by dt, 3 minus 3 over 3t minus 1, divided by x dash, which is simply 3. So this one's pretty easy because I've got 3 as a factor in here and here. So that equals 1 minus 1 over 3t minus 1. And I want to figure out where that is equal to 1/2. So as I showed you in class yesterday, if you just step back and take a look at this, you can see you've got 1 here and you've got 1/2 here. So we can combine up the constants, so collect up your like terms, and we'll get 1/2 minus 1 over 3t minus 1 is equal to 0. So 1/2 is equal to 1 over 3t minus 1. Now just looking at it, we've got the same numerator, so we must have matching up denominators. So 2 has to equal 3t minus 1, 3 is equal to 3t, and t equals 1. So what we've got now is we've got the t value that is going to make the gradient be 1/2, but we haven't yet got the coordinates of the point on the curve. So we're going to take t equals 1, and we're going to substitute it into my original equations. So x is going to equal 2 plus 3 times 1, which gives me 5, and y is equal to 3 times 1 minus the natural log of 3 minus 1, which is 3 minus the natural log of 2. And so if you want to give those coordinates, you could either write them as 5. Did it ask for exact values? No, it didn't. So the exact value is that, and the approximate value is 5, and I got 2.307 to 3 decimal places. Okay, so that's the basics of how parametric works. That's a question where we just have to do the first derivative. That's a merit question. Once we get to doing the second derivative, we're usually up to an excellence question. So I'll do an example of a second derivative parametric in the next video. Okay, let's look at the second one, which is about stationary points and the nature of the points. And this also is from last year's exam. Now, this one actually was an excellence question. And I think it's a pretty straightforward excellence question as long as you understand what a point of inflection is. So we're told that if p is a positive real constant, we have to prove that this, I'll make it a bit bigger, y is equal to e to the power of px squared does not have any points of inflection. So what does it mean for something to be a point of inflection? Well, let's take a look at kind of your classic curve that's got a point of inflection. We saw this in class yesterday. This is y is equal to x cubed. And here, if you take, I'm going to take the ruler and show you what's going on with the gradient. When we're moving along here, you can see that the gradient's positive, but it's getting smaller. Okay, now here at the origin, it's changing, right? So it suddenly switches back to the gradient being positive, but getting steeper again. And that idea of the gradient changing, staying positive, but changing kind of in strength is what a point of inflection is about. So to find a point of inflection, we set the second derivative equal to 0. That's not enough to conclude that something is definitely a point of inflection. We have to check the gradient on either side. But it's going to be enough for what we're asked to do here. Because what we're asked to do here is to say, we have to prove that this does not have any points of inflection. So if we can show that there are no solutions to this equation, then we will be done. Right, so to do a proof like this, you should have some decent communication about what we're trying to do. So I'll just find some blank space. I'd start by saying, for a point of inflection, we need, and you can either say this, or you could say we need f dash dash of x equals 0. We know that p is positive and p is a real number, and y is equal to e to the px squared. So we're going to investigate the second derivative of this function. So firstly, doing the first derivative, dy by dx is going to equal e to the power of px squared times the derivative of this function here, which will be 2px. Now I did that quite quickly using the chain rule. If you're just starting out with the chain rule, I'm going to do it again, but more slowly. So this is the idea of the inside function and the outside function that we talked about yesterday. So y is equal to e to the power of something, and we'll call that something u. U is equal to px squared. So du by dx is equal to 2px, and dy by du is equal to e to the u. And you can look that one up on your formula sheet if you need to. That means that when I put it all back together, dy by dx is equal to dy by du times du by dx, which gives me e to the u times 2px. And now we can substitute that u back in. So that's e to the px squared times 2px. And I really would prefer to write it like this. Got to get the pen to work. There we go. Equals 2px times that. Okay, so that's the slow working out with the chain rule. And it's absolutely fine to do it like that to start with. But most of you, I think, even yesterday, if you were seeing it for the first time, were able to think about it more quickly as e to the power of something, and then does something is a function of x. So we have to differentiate with respect to the inside function. Okay, so that's the first derivative. Now we've got to find the second derivative. So notice that now what I've got is I've got a product. This is a function of x, and this is a function of x. So my second derivative is going to involve the product rule. So dy by dx is 2px e to the px squared. We'll call this one u and this one v. And again, I'm going to do this without writing out all the uv stuff slowly. So first we're going to have u 2px times the derivative of this one, v dash. And we've just done that. That was the point of the first half of the question. And now I'm going to switch it the other way around. Right, so this is u times v dash. And now I'm going to have u dash, so 2p times v. Remember, what I'm trying to show is that this can never equal 0. So usually the strategy here is going to be to clean it up and to factorize. So we have 4p squared x squared e to the px squared plus 2p e to the px squared. Looking at this, you can see that we've got a common factor here, and we've also got some kind of common factor with the 4 and the 2 and with the p stuff. So there's a lot of common factoring that we can do. We've got 2p e to the px squared. Now we have to times it back by 2 to match the 4, and we have to times it by another p, and we have to times it by x squared. So that's all good. Just check that that matches up. So we've got 4p squared x squared times that. And here we've got exactly that there. So it's going to be this. Right, so we've got to show that this can't be equal to 0. So we know that 2p is greater than 0. And we know that e to the power of anything is, let's see, did they tell us? Yeah, so p was strictly greater than 0. So e to the px squared is strictly greater than 0. Now, the next thing to look at is this. 2px squared is greater than or equal to 0. And 2px squared plus 1 must be greater than or equal to 1, which is greater than or equal to 0. So what have we shown? Well, we've shown that this is greater than 0, because this can't ever be 0 and this can't be 0. So it's greater than 0 for any x. So no solutions to f dash dash of x equals 0. So no points of inflection exist. All right, I thought I might get through a third question, but this video is 13 minutes already, so I'm going to stop there and upload this one, and then do the next one. Will have implicit and then more implicit. Thanks for watching. Leave me a comment or shoot me an email if you've got any questions.